Hello students, welcome back. We just completed section 2, which covered linear congruence. Now let's go to section 3 and study systems of linear congruences. Here's a motivating example. Let's consider these two systems. 3x plus 4y is congruent to 5 and 2x plus 5y is congruent to 7, both modulo 13. And the second system, exactly the same, but this time mod 14. So what's the difference? Mod 13 versus mod 14. And what's the similarity? Of course, the left-hand side. And then that's not all. As a matter of fact, I'm recycling this even once more. Mod 12 this time. So we have to answer this question here. What's the difference? 12, 13, and 14, of course, they're different. But my real question is, of course, what difference do they make? What's their contribution? The similarity part is a little bit easier to understand, but that too will become a problem. So please remember these two questions. All right, now let's go back to the first problem and solve it. That's not too bad, as a matter of fact, because solving a system of linear equations is something we have been doing for a really long time, and we can use pretty much the same technique. Multiply 5 to the first line and multiply 4 to the second line to remove y, and that's the result. Yeah, 5 times 3 is 15, 5 times 4 is 20, 5 times 5 is 25, that's you get first line. And then 4 times 2 is 8, 4 times 5 is 20, 4 times 7 is 28. That's how you get the second line. By design, 20y is common, so subtracting one from the other, we get this. 15 minus 8 is 7, 25 minus 28 is negative 3. All easy, all simple. And mod 13 did not kick in yet. Now, if this had been just a sum of linear equation, then you're not going to get this mod 13 and just the equality only, so that you get, that's what you're going to get. And therefore, that's going to be your solution. Well, good. And then you can continue doing whatever you want to do for y. But we have a problem here. Unlike the system of linear equation case, we cannot divide freely. Here, I want to divide 7 away, but I cannot divide and create a rational number because this is mod operation. So instead of dividing and creating a rational number, we have to divide by multiplying its multiplicative inverse, modulo 13. What is it? What is the multiplicative inverse of 7 mod 13? Well, time's up. It is 2. 7 times 2 is 14, and that's congruent to 1 mod 13. So basically, we are multiplying 2 to both the left-hand side and right-hand side. Let's go back to the previous equation here, previous modular equation here, and multiply by 7 inverse to both left-hand side and right-hand side. In the left-hand side, 7 inverse times 7, they collide and disappear. They just become 1, so we have just x. In the right-hand side, 7 inverse times negative 3. So 7 inverse is 2, so 2 times negative 3, which is negative 6. Consequently, we have 7. So the answer is 7 mod 13. We can do something similar for y, and if you do that, this is the computation you're going to get. Curiously, 7 inverse shows up again, and the answer is 2. So multiplying by 2 times 11, you get 9. So the answer, x is 7 and y is 9. We get that, but that's not very important. The really important key point is dividing 7 away. We have 7 inverse, and curiously, 7 inverse shows up again for y as well. Is this a coincidence? Or are they always the same? Something to think about. All right, That's the solution for the first problem. How about the second problem? Well, the same thing here. So let's proceed with exactly the same technique. Eliminate y. Exactly the same thing. And then we have to divide 7 away. So I cannot divide by 7 and create a rational number. So I have to multiply the multiplicative inverse of 7 modulo 14. What is it? 7 inverse is? Well, there's a problem. It does not exist in this case. Previously, 7 inverse existed, and it is 2 mod 13. Now 7 inverse does not exist, mod 14. What's the problem here? What makes the difference? Why 13? Why not 14? Here's the answer. 7 and 14 are not relatively prime. 7 and 13, they're relatively prime, so no problem. We have multiplicative inverse. But 7 and 14, no, in that case, no. So if you try any x, 7x equals to negative 3, it's not going to work. Or more precisely speaking, 7x is congruent to 11, because negative 3 is congruent to 11. Try any x. 7 times 0, 7 times 1, 7 times 2, all the way up to 7 times 13. None of them will give you 11, modulo 14. So no solution. And same for y, no solution. And again, maybe by some strange coincidence, we have the same problem, 7. I have to invert 7. I can't do that modulo 14, but yes, I can do that modulo 12, modulo 13. So a coincidence, or is 7 really a fundamental quantity here? Well, if you have to solve an individual problem, then you can just go ahead with elimination or maybe substitution, whatever you like. So that's not going to be too much of a problem. But if you consider a theory, then there's certainly something to think about. Why 7? Well, let me give you the answer. It turns out that the determinant of this equation obtained by crisscross multiply the principal diagonal 3 times 5 minus the other diagonal 4 times 2, and that is 7. 3 times 5 is 15, and 4 times 2 is 8. That's 7. And that's the reason we have the recurring theme of 7 inverse. 7 inverse worked out okay for 13 because 7 and 13 are relatively prime. It didn't work out for 14 because they're not relatively prime. One more problem down here. For mod 12, yes, it'll work out because 7 and 12 are relatively prime. Why does this determinant come into play? Let's answer the question, and that goes a bit toward linear algebra, even though you must have gone through something similar in pre-calculus classes, matrix multiplication and stuff, but I don't know how much you know about those. So this part, if you have linear algebra background, you'll feel comfortable. If you don't, then it's still a good idea to stay in, and because after all, you should have some knowledge on matrices and matrix multiplication from your pre-calculus. So okay, all right. So partly optional, partly required topic. So this ax plus by equals to s and cx plus dy congruent to t, that thing can be re-expressed as a matrix multiplication like this. How do you do matrix multiplication? The first row times the column, and then the this computation is done by dot product. First times first plus second times second. A times x plus b times y. So that's what we have here, and that's the first entry s. And then we do the same things to the second line. Second row and this column, first plus second. So c times x plus d times y. That's how you get that. And that's the second line. So we have this matrix expression, which is equivalent to the original expression. Now our aim is to flip this matrix multiplication over to the other side. How can it divide it away? Well, we want to multiply the multiplicative inverse, which we call the inverse matrix, and that inverse matrix looks like this. And then this point here, which we call adjoint matrix, doesn't look too bad, just switching the order of principal and some negatives on the other diagonal. And in general, the adjoint part does not involve division. But this one here, we have division of this determinant, AD minus BC. And that inverse exists if and only if this determinant, AD minus BC, and M are relatively prime. Remember that? Modulo inverse exists if and only if the non-zero number, and the modulus are relatively prime. Remember that? And once the modulo inverse exists, it's unique modulo M. So that's where we use the relatively prime condition right here. And as for this entire quantity here, if you're comfortable with the linear algebra, you must already know. But in case you don't, let's have a proof. It's going to be really a brief sketch of proof. So what we want is this matrix expression of the equation, or congruence equation, into this form, flipping over, and we get inverse matrix there. And we want to prove that inverse matrix is this. So we just go ahead and multiply them together. Multiply the adjoint matrix, this thing, to the original matrix, and do the matrix multiplication. First row times first column, AD minus BC, so we have that. First row times second column, DB minus BD, that's 0. Second row, first column, negative CA plus AC, so that's 0. Finally, second line, second row, and second column, AD minus BC again. So take AD minus BC out, and we have the identity matrix 1, 0, 0, 1. Therefore, dividing this one away, we get the inverse matrix expression, and we can do that if and only if the determinant AD minus BC and M are relatively prime. Remember the modular inverse condition. So inverse matrix is this thing here. So if I flip this one over to the other side, that's the inverse matrix. And that leads to this conclusion. So we have the unique expression of the answer, modulo M, and that's valid when we can divide AD minus BC. In linear algebra, or perhaps even in pre-calculus, maybe you went through the same formula. Over there, we of course use equality, and instead of this, we had 1 over AD minus BC. Remember this? For rational numbers, we can do that. For real numbers, for complex numbers, everything works out. But for congruence mod M, we need to go through with this GCD condition, and that's because of this modular inverse condition. So much for the required part. We're going to come back and discuss a bit more in an optional video.